everyone, and welcome to Circular Motion. It's time to start spinning around and seeing what we can learn about physics and things that rotate and go in circles. Just a few definitions. So you see the definition of rotation. You might think of another example besides a spinning top as maybe like an ice skater spinning around when she's doing that real quick circular motion when you saw that during the Olympics. And then when it comes to revolution, when you think about an external axis, you got to think about the fact that the Earth moves around the sun, but the center of that motion is the sun, so the axis is outside. Another word that people use instead of revolution is sometimes they think about orbiting. So some of you folks out there might be fairly athletic, and you may have run around a track once or twice. So let's see if we can use that example to compare tangential speed and rotational speed. If you're running around a track, your tangential speed would be to measure the distance that you ran and divide that by the amount of time that it took. And since we're talking about circular motion, I know most tracks are oval, but if we were going to take the circular motion of what you did, we would multiply 2 times pi times the radius of the track. So if it happened to be a circular track, we could get the radius from the center to the outside, and then we could take that distance and divide it by the time, and that would be our what we call the tangential speed. The rotational speed would be the number of times that you ran around the track per unit of time. So if there were a race going on and it were the 400-meter dash, then everyone would have a rotational speed basically of probably one rotation per unit of time. But the tangential speed would be different for everyone because they would cover the same amount of distance, but they would do it in different increments of time. So I might be dating myself here a little bit by talking about a record player. So if you had a record player and you were standing in the exact center, you would have no tangential speed, but you would have rotational speed. So in the center of that circle, you would have 0 tangential speed because you don't have a radius. But if you were outside the circle, if you were moving on the outside, out in this area, because you do have a radius, you would have a tangential speed on the outside, but not if you were right in here. But no matter where you are, whether you're in this location, or this location at the radius, at the center, you're always going to have a rotational speed because you're still going to turn in a circle, whether it's that size or whether it's that size. So the bigger the circle, the farther you are from the center, the greater your tangential speed. So if you're out here on the edge and you're moving in a circle, you're going to have much more tangential speed than if you're right here rotating and moving, because you're going to have a smaller radius on the inside than you would on the outside. So here's our first formula. So here you have our first introduction of something called centripetal force. So as you're spinning something, as something is rotating, there's a force that keeps the object moving in a circle. And you'll see some demos in class about this, and you can probably look at some online. So as something is spinning in a circle, something keeps it from flying away, and that something is a force. And it could be a visible force, like maybe a rope or a door pushing somewhere, Or it could be something that we don't really notice, like friction. But in any case, centripetal force is the force that keeps an object moving in a circular motion versus flying away as it's moving. And if you look at the formula, hopefully it won't seem too complicated. I know that you recognize most of the letters. You might not think about that AC. The C just means that we're talking about an acceleration that's in a circular motion. So that's not acceleration due to gravity, and it's not acceleration in a linear fashion. It's acceleration in a circular motion. So that's what makes it a little different. But m times v squared, that's a v, divided by r, can give you the force needed to keep something moving in a circular path. So here's an example. So we have mean old Goliath. He's been taunting the Hebrews for many, many years, and he's a big giant. Now David, being a shepherd, had a slingshot. Slingshots back then were not the same kind of rubber where you pull back and you let something go. A slingshot back then was more like a leather strap, maybe a long leather strap, and it had a pouch in the middle. And what you would do is you would just pick up the rock, put it in the pouch, and you'd swing this leather strap above your head. And if you were a shepherd, you had to make sure that your sheep were safe. So you got to scare the wolves away, or the bears, or the lions. But don't be scared. This is just an example. So he would swing this leather strap with a rock in the pouch as fast as he could, and then he would release the leather strap, one end of it, and the rock would go flying out. And that's basically about the tale with David and Goliath. He swung this rock and hit Goliath and killed him. Well, let's actually put some math to something here. So the first thing we're asked to find out is what would be the speed of that rock when it comes out of that slingshot? So to find the speed, we have to find the velocity. Velocity is to take the distance, which is 2 pi r, and divide it by the time. So 2 times pi times the radius, which was 0.8 meters, that's the radius, and then we're going to divide that by the time of that rotation. And when we do that, we get 12.5 meters per second. So that's the tangential speed of the slingshot. To find the acceleration is to take this velocity squared and divide that by the radius. So we're going to take 12.5 and we're going to square that, and we're going to divide it by the radius. So when we do that, we get a pretty large number, 195, and we'll round that off to 0.3, and that's meters per second squared. That's a pretty hefty acceleration. Well, now let's look at the force that David was able to give that rock by spinning it at that acceleration. So the force is equal to the mass times the acceleration. And the mass of the rock was 1.5 kilograms. And we're going to multiply that by the acceleration of 195.3. So when we do that, we get an answer of 292, well, about 293, because it's 0.95 newtons. So that's a pretty hefty hit, and that's why Goliath is here, and David, who was much smaller, became very celebrated in the lore of the Hebrews. So let's revisit this number again, the 293 newtons. That's the amount of force that David had to use to hold that rock in place while he was spinning it. And as soon as he let go, then that's the amount of force that he was able to deliver when it came to an impact. So that was the force needed to keep it in a motion, and when he let go, he had some mass and acceleration with that rock, and it made an impact. The center fleeing force is called the centrifugal force. This is not really a real force, and we'll talk about this in just a second. So as David was spinning that rock above his head, that rock wanted to fly away. He had to use a force to keep it in the pouch as he was spinning it. That rock wanting to fly away is what we would call the centrifugal force. But there was nothing pulling on it and nothing pushing on it. It just wanted to fly away because of its inertia. You have an object that's spinning and it wants to keep spinning, but you have to use a force to hold it in place. And that's what inertia was keeping that rock from, the inertia was making that rock want to fly away. But David had to hold tight. And when he let go, the inertia of that rock allowed it to fly away from the slingshot. Our final concept dealing with circular motion is called torque. So if you look at the definition of torque, it talks about the force being perpendicular, a lever arm, and something called a fulcrum. Well, the lever arm is basically from right here to right there. That distance right along that path is the lever arm. And on this side, it's maybe that side to this side, as long as the force is being applied at the end. This little spot right in here is the fulcrum. That's the pivot point. And if you have a force pushing down on this end and a force pushing down on this end, if those forces are equal and the distances are equal, nothing's going to happen. Let's take a look at an example. So if this child's torque is equal to this child's torque, then we won't see anything happening. So if the torque on the left side is the same as the torque on the right side, nothing really happens. So let's look at what that might look like mathematically. So if you have a boy sitting on one end of a seesaw, he has 600 newtons of force pushing down. And if the pivot point is right here, then his lever arm is 1.5 because he's that far from the fulcrum. So where would somebody that has a weight of 400 newtons need to be to make this thing balance out so that they don't tip over? Well, let's find the torque on this side. We see that the torque on this side is equal to 900 Newton meters. So to make this thing balance out, this side also has to be 900 Newton meters. So 400 times what distance is going to give us 900? And we can just basically say 900 divided by 400, and that gives us 2.25 meters. So this person has to be 2.25 meters to make it balance out. And if the child were to sit at the 2 meter mark, so that's if they sat at the 2 meter mark and the other child stayed where he was at the 1.5 meter mark, we know that that was equal to 900. There's more torque on this side than there is on this side, so the seesaw would go down and this side would go up. And that's what makes him rotate.